Welcome to the next session on microprocessor and microcontroller. I would like to continue from where Ramesh Babu left yesterday. He mentioned about the segment register, saying that there are 4 segment register, there are core segment, data segment, stack segment and extra segment. These segments are 16 bits wide, and the external bus whatever is available on an 8086 and 8088 microprocessor address lines is 20. Now let us look into how these particular address are being calculated and how the microprocessor generates the 20-bit address. Segment registers are being shifted left by 4 bits or multiplied by 10 hexa, added to an effective memory address. When I say it is added to effective memory address, the memory address whatever we have can be calculated or can be taken from different sources, based on which we have different addressing modes and which we will discuss in times to come. After shifting this by 4 bits, as it is represented in the slide, the segment register are displaced by 4 bits and the least significant digit would be 0 hexa, but converting into binary, since it is rotated 4 times to the left, we have 4 zeros, and following it all is being represented as XXXX. This particular value of X, 4x is another digit, the next 4 digit bits are another 1 digit, another 4 bits is another digit. So basically these are representing the total of 16 bits, with the least significant 4 bits being 0, and the effective memory address which is being given either by instruction pointer to access the code or accessing data, and using data segment and extra segment we have registers such as BX register, source index register, destination index register, which has already been mentioned, saying the application of these registers is to access the memory. And if you want to access the stack memory location, again the stack memory address is 20 bits. We have stack segment which is being displaced by 4 bits to the left and added to either the stack pointer or it is added to base pointer. It is possible that stack segment is displaced by 4 bits and added to stack pointer and base pointer added together to get the total physical address. So adding displaced segment register with the effective memory address, we get 20 bit, which is mentioned here as P, so that we know that the total address what is being generated is 20 bits for the memory location. So as just mentioned, code segment points to a particular memory location and this displacement is through instruction pointer. So when you are trying to talk about data segment and extra segment, the effective address can be from either directly the address can be given, which is mentioned as direct. It can be registered indirect, that means the content of BX can be added to the data segment which is displayed, or SI or DI or BP. And index register, it can be SI with 8 bit or 16 bit of data, or DI plus 8 bit or 16 bit of data. When you talk about BX register, we are trying to add the base register BX plus 8 bit or 16 bit of data and BP with 8 bit or 16 bit data. So that means that we have a combination of registers which are being added to get the required result. The other option is base index, trying to talk about both base register and index register can be added to get the required address. So this is mentioned here that BX is added to SI, or BX is added to DI, or BP is added to SI and BP is added to DI. Now as it's been mentioned here, we have a specific set of registers being added to some specific set of registers to get the effective address, which is going to give you the total effective address added to the displaced segment register to get the required results. Now this type of operation, whatever is being mentioned, base index relative, earlier we have mentioned this as base indexed, the other one is based, or we talk about indexed, or we talk about register indirect, or we talk about direct. See, these are all the mechanism which is being adopted by the microprocessor to access a particular memory location. This process of trying to calculate the address, we call this by a name called as an addressing mode, which we will discuss in coming sessions. Now let us go to the last part where we are trying to talk about the stack segment having only SP and BP register being used. Now, as has already been mentioned in the previous class, stating that the segment registers are 64 kilobytes. The diagram here shows that there are different combinations of operations that are possible when you are trying to perform the calculate the required address, or each segment can have 16-bit added with the effective address to give the physical address. So, at any instant of time the microprocessor can have as 4 segments where it can be continuous memory location, or it can be partially overlapped, or it can be fully overlapped, or it can be disjoint. What does this mean? It means that when you are trying to talk about the memory location, we have starting from 0000 to FFFF. This is 1 megabyte of memory. So, we have segments which is of 64K, which is possible to really interact with. So, this 64K can be for different segments, and these segments can be either the code segment, or it can be for data segment, and it can be for extra segment and stack segment. Now, this is what it was mentioned earlier, but the point is it can overlap also. When I say it can overlap, I am directly trying to say that along with data segment there is an overlap for the code segment. Similarly, we can also have extra segment and stack segment overlapping. That means that if you initialize the segment register with the same starting address, and it means that it is possible that you can have an overlap. This process of trying to talk about having overlap causes certain type of a problem. If you use one segment and write it, and in using another segment again writing onto the same location destroys the contents of the memory. So, this is not a very good practice as such when you are trying to talk about you initializing all the segments with the same address. Now, let us look at a general operation which is being shown in this particular figure. Core segment has a particular address. It is possible to access a segment of 64K. Data segment can have another separate segment where there is no overlap, but you can also have data segment initialized as shown here with a partially covered, and similarly the stack segment can be overlapped or can be independent. Similarly, extra segment can be separate or it can overlap with the stack segment. So, this is a general figure which is being mentioned to make you understand that how these segments can overlap and perform the operation. Having understood the fundamental of trying to say that the memory are in segmentation and it is possible to access the location, let us now look into a simple problem of trying to tell how do you calculate the physical address of a given processor when you have the effective address and the segment address value given. So, it is a simple example. Given that the effective address of a datum is 2359 hexa. See, I do not usually call this as 2359, it is usually used in decimal number system. Since we are trying to talk about hexa decimal number system, it is always better to mention it as 2359 hexa, and the data segment is 490B hexa. So, we mentioned the data segment having the value as 4 490B hexa, and we have the effective address to be equal to 2359 hexa. Now, when you add these two directly, it so happens that we will not get 20-bit address. So, the data segment has to be now displaced by 4 bits. Displacing by 4 bits is nothing but multiplying by 10 to get the value as 490B0 and adding 2359 gives you the physical address. So, this is an effective address which is being given, and this is the segment value whatever is being given. So, we get the total physical address which is set onto the bus to access the required data. This is an example which is being shown, and the total result what you get is 4B409 hexa. Now, let us take up another example. If a physical branch address, so the branch address is given to be equal to 5A 20230 hexa, and the code segment is given as equal to 5200. Now, if the code segment is changed from this to a new code segment value which is 7800 hexa, the question is what will be the branch physical address. Now, let us, having understood this, we need to first find out what is the effective address. Once you get the effective address, take that particular effective address, add it to the displaced new code segment value which is given as 7800 to get the required results. So, let us look at it. So, when you get the offset which we are trying to calculate, the given physical address is 5A230 hexa. Now, calculating this, we get the offset to be equal to 8230 hexa. The new segment value is 7800, displace it by 4 bits, add it to 80230, we get 80230 hexa. This is the physical new address what is required. Now, having understood this basic part, I think it is necessary for us to know in detail about the pins that are available in 8086 before we go to the remaining part of the program. And the best option is to look into the internal pin configuration of 8086 microprocessor. 8086 microprocessor basically has 40 pins. I will not be discussing about the ground and VCC because we have 2 ground and 1 VCC which is about 5 volts is being given. I will be concentrating basically on the remaining pins that are necessary for 8086 microprocessor to interface to the external world. Why is that we need to know about the pin configuration? Once you know the pin configuration, it is possible for you to interface to the external device. So, the best option what we are trying to talk about is try to understand how this particular pin configuration being arranged. So, 8086 has got basically 16 address lines, but 20 data lines. Of these, sorry, it is reverse, it is 16 data lines and 20 address lines. Of these 20 address lines, first 16 address lines is multiplexed with data lines. So, when I say it is multiplexed, it so happens that both these lines are common. First 16 address lines are common to data lines. The way in which it works is we call it as multiplexed. That means that these lines operate at different instant of time for different application. Once during the complete operation of 8086 microprocessor is divided into states called T1, T2, T3 and T4 states. Each of these are 1 clock period duration. The other states in which the microprocessor works is T hold, T halt, T reset and T wait. Let us not bother about these states for the time being, because they work on integral multiple clock periods. When I say it works on integral multiple clock periods, it can be 2 or it can be 10 or it can be 20 based on the situation. Now, when I say T1, T2, 3T, 3-4 or the 3-4 clock periods during which the microprocessor performs the required operation to the external world, during the T1 state of the microprocessor, it uses the address data line, which is called address line and data line, which we are trying to show separately, and during T1 state it always has the address. It has the address, and during the remaining period of the time it will have the data. So, we are trying to say that these lines AD0 to AD15 are 16 address lines. During the T1 state of the microprocessor, these lines are used for address. The remaining time these lines are used for data. Now, as the time is being given for an address, this address is going to be lost after T1 period, and this data has to be latched and it has to be stored somewhere. So, we have a signal which we will be talking about shortly, saying that this signal enables the processor to take these address lines sent to a particular latch, and this latch has to be designed by the user. So, we have other lines called A16 to A19, which is multiplexed with other status signal S6 to S9. So, that means that all the lines A0 to A19, that is 20 address lines, are being multiplexed with the data lines D0 to D15 and S3 to S6. There is another important signal called as a BHE bar signal. This is called bus high enable signal. This particular bus high enable signal is being used whenever 8086 microprocessor is interfaced to the external world. It has the signal has is available during the T1 state. During the remaining period of the time, you have the status signal S7. The complete operation of 8086 is based on the clock. The clock that is being generated has to be 33% duty cycle. When I say it has to be a 33% duty cycle, it means that this particular clock, whatever is being generated, has to be 1/3 period of time high and the remaining period of time it has to be low. Only then we call this one as 33% duty cycle. And this particular clock frequency, to generate a signal of this sort, has to be interfaced, and we have another chip which enables it to do, that is called as 8284 clock generation chip. So, along with it we have a reset signal. A reset signal is being used to reset the microprocessor. When the microprocessor is reset, all the registers it has got is set to equal to 0, except the core segment register is made equal to FFFF hexa. So, we have a ready signal. A ready signal is being used by the microprocessor especially when the external device is not ready and it wants to slow down the complete operation, especially IO devices. The microprocessor is very fast based on the clock whatever is being given, and to reduce the speed of the microprocessor is not possible. So, external device says to the microprocessor, you wait. Under such circumstances, the microprocessor goes into a state called as T wait state and will be monitoring the ready signal. As soon as the ready signal becomes low, stating that the device is ready, it comes out of the ready state and immediately executes the remaining states and continues the instruction. There is a signal called as read bar signal. This is a signal to tell the external world, stating that the microprocessor is performing a read operation. The read operation takes place during the T2 state when this signal becomes low and becomes high during the T4 state. Now, this is a signal that is given by a ready signal, and ready signal becomes low during the T2 state, and it tells the external world that the microprocessor is going to read the data either from the memory or for the IO device, and when it goes from low to high, the data must be made available on the data bus. We have a signal called as test bar signal. Test bar signal is being used to tell the external world, stating that the device is ready to perform the required operation. We will go into the details shortly about this test bar in the coming slides. I will explain to you in detail. We have two important signals called as interrupt and non-maskable interrupt. These are the two signals, INTR interrupt and non-maskable interrupt. These are the two signals which are being used from the external world to interrupt the microprocessor when it is performing an operation. We discussed this again when you are trying to talk about the interrupt service routine and the process, how the microprocessor stops the executing the present instruction and goes to the new instruction called interrupt service routine and performs using this particular operation. We have certain set of pins that are unique for a different mode of operation. 8086 can work on two modes of operation. One is maximum mode, the other one is minimum mode. We have a pin here called MN by MX bar. MN stands for minimum, that means that when this signal is high, the microprocessor works in minimum mode. When this signal is low, this microprocessor works in maximum mode. What is this minimum mode and maximum mode? The microprocessor, when it is in the minimum mode, uses only the microprocessor chips and it does not look for any other processor along with it. It means that it is a standalone chip having certain chips that makes it compatible to work, like clock generation chip and IO chip, which enables it to really send the signal and receive the signal. When it is in the maximum mode, we can work along with 8086 microprocessor, the other coprocessor like 8087 math coprocessor. So, the math coprocessor is much more powerful and performs the operation much faster, and hence we have a math coprocessor that enables it to do the operation much fast. Now, let us look at what are the signals. There are about 8 signals the microprocessor has when it is in the minimum mode. They are DEN signal, which is being mentioned in the slide as S0. So, the S0 is a status signal which is being given for the maximum mode. Let me discuss that later. For the time being, let me discuss only about DEN signal. DEN stands for data enabled signal. This is being used when the microprocessor is connected to the external world and you want to really say that the data has to be sent or received either to the memory or for IO device. We have here a chip that enables the bidirectional bus, data bus, to send the data to the external world or receive the data to the external world. The DEN signal, DEN bar signal, enables this particular device to be selected so that the data can be transmitted or it can be received. Now, we have an important point to note. Why do you require a separate chip, especially for the bus to transfer or receive? Whenever you are trying to talk about microprocessor is a very powerful and delicate device, and we think about a lot of external devices that is going to be connected. It can be power supply devices like stepper motor, or it can be something like a relay switch, where the relay one side we are connected to the microprocessor, the other part is connected to the power supply. Whenever it is being connected to the external power supply, it so happens that if there is any short, there may be a problem to the microprocessor. When you are trying to use a buffer, this buffering device can either stop the signal damaging the microprocessor, it gets damaged, which is much more cheaper and it could be replaced. So, we have a signal chip that is being connected, and this chip is being enabled using data enable signal, and we have another signal called as data transmit or receive bar. This is a signal that enables this particular device, which we call as a transceiver either to transmit the data when this particular signal is high. D transmit is saying that you are writing it onto the device. When it is low, the data is going to be returned into the microprocessor through this particular chip. So, we have a signal along with it. So, this dt by r bar signal has the another signal which is S1 bar only when it is in the maximum mode. These signals, whatever I am trying to talk about, is in the minimum mode of operation. These signals are in the maximum mode of operation. So, let us look into the other signals whatever we have when you are trying to talk about the operation of 8086 microprocessor. So, the next one is memory or IO device, memory or IO device signal, memory/IO bar. This is a signal which is being used to differentiate between a memory device or an IO device. Whenever this particular signal is low, then it says that it is interacting with an IO device. If this particular signal is high, it says that I am going to interact with the memory. Now, this is a chip which has an separate space for memory and separate space for IO, whereas some other microprocessor like Motorola chip has only one memory space exclusively for memory, no space for the IO device. So, we talk about 8086 microprocessor having something like 1 megabyte of memory, and it can access 64K IO devices, and hence we have a pin that differentiate between memory and IO device. We have a signal called ALE signal, which has another signal called KS0. The same pin is being used for both the purpose. When it is in the minimum mode, it uses as an address latch enable signal. I was mentioning about this particular signal quite some time back, trying to say that we have an address data bus D0 to D7, D0 to D15, which is multiplexed with AD0 to AD15. This AD0 to AD15 has to be captured using a latch, and this latch will store the data or whatever is being said during the T1 state by using ALE signal. ALE signal basically means address latch enable. It enables the latch so that whatever is the information that is coming onto the bus is going to be latched into it during the T1 state, and it is made available externally for the device after T1 state, because after that period of time the line becomes tri-stated and then it will have data in it. At that time this line should not have anything else, only the address should be available. Hence we have a situation of having a latch. That latch is going to be used by the device by sending an address latch enable to store the address, and it becomes convenient for the external device, either a memory or an IO device, for interaction. The next one what we have is interrupt acknowledge signal. This particular signal, interrupt acknowledge signal, is linked with INTR signal. I was just mentioning earlier saying that I will be talking about this particular INTR signal later. INTR signal is an interrupt signal which is being used by the microprocessor for stopping the present execution of the program and start executing the interrupt service routine. Now, when a device sends an interrupt, external device says that it wants to interrupt and take control, it sends a signal to INTR pin. microprocessor which will be monitoring this particular pin. At the end of the present mission cycle, it recognizes the interrupt provided it is not masked. In the pin configuration, we in the internal architecture of the microprocessor, we mentioned stating that there is an interrupt flag. The interrupt flag, if it is equal to set 1, that means that INTR is masked. Only when it is 0, INTR is enabled. Once this is enabled, the microprocessor is now interrupted. Once it interrupts, this particular interrupt is maskable interrupt. It is a maskable interrupt. The other important point which you have to understand when INTR interrupt comes is non-vectored. It means, when I say it is a non-vectored, it means that it does not know where to start executing the program. So, when an INTR interrupt comes into the microprocessor expects the device which is interrupting to give the address from where it has to execute. So, what microprocessor does is it sends an interrupt acknowledge signal to the external world. When the interrupt acknowledge signal is sent to the external world is nothing but the signal that has to be used by the IO device to provide the interrupt type. There are 256 interrupt types. One of the interrupt type number has to be provided to 8086. During the second interrupt acknowledge mission cycle, the device which is interrupting has to place on the data bus the interrupt type. When it places the interrupt type during the second interrupt acknowledge mission cycle, the data whatever is given is taken in by the microprocessor, calculates the address from where it has to executing the program by multiplying it by 4. So, this interrupt type is taken, multiplied by 4, goes to a particular location where the address is given for executing the program, takes this address, puts it to the register and start executing the interrupt service routine. Now, we have the next one called write bar signal. The write bar signal is being used. Write bar signal is used by the microprocessor to tell the external world that it is writing the data. So, that means that whenever 8086 writes the data, obviously we know that dt by r bar becomes high, telling this particular chip saying that the data is going to be written, and write bar is being made low to tell the external world to now read that particular data what is being sent by the microprocessor. Whenever we talk about 8086 microprocessor, we talk about this particular processor is the main. It says it is going to write to the external world, it is going to read. So, when I say that write, it is the processor which is going to write onto the external device. Next, we have what is called non-maskable interrupt. Non-maskable interrupt is again an input signal which is being used for special purpose like security. Say for example, if the power goes off, if there is a calamity fire. So, this type of system, there is an interrupt telling the 8086 microprocessor that there is a calamity. There should be an interrupt service routine that has to be written. This interrupt service routine enables the processor to execute a set of program to set things right or to send an alarm. So, this means it is not maskable. When I said about INTR pin whatever is being said is an interrupt pin which is being used to interrupt the microprocessor which is masked, whereas non-maskable interrupt pin is a pin which is not possible to mask. We have two more important signals that is being provided called hold and hold acknowledge. The hold and hold acknowledge are the two important pins that is being provided to interact with the external world to directly access the memory. It says that hold is being given from the external world to the microprocessor, and hold acknowledge is a signal sent from the microprocessor saying that it accepts it. Let me briefly explain about these two pins that makes it much more clear for you to understand. So, one is HLD hold, and the signal what we have along with this is request 0 by grant 0, and HLDA request 1 by grant 1. Now, hold is a signal that is being sent from the external world asking the microprocessor to relinquish the bus. Bus is address bus, data bus, and also the control bus. When the device requests the microprocessor to relinquish the bus, it means that it wants to become the master and it wants to take control of the system, that is the memory and IO device. Usually the memory device to write fast, this direct memory access is being used. Directly the device interacts with the external world through by making the operation of sending the data to the memory directly. So, that means that the device will send a hold signal, to the microprocessor. The microprocessor, after it receives this signal, completing the mission cycle, it says that it will tri-state the bidirectional data bus and the address bus, and then sends and hold acknowledge signal saying that yes, have tri-stated the bus is available and the memory is available for its operation. The DMA device will interact with the memory. After interacting the memory, then what it does is it makes the hold signal inactive, 0. Microprocessor, after relinquishing these buses, it will then say that this particular device is using my bus, and as soon as it relinquishes, it gives back the bus. I would like to continue, hence it will be monitoring this particular hold pin. Once this device relinquishes the bus back to that means that 8086 get back this particular bus. It understands by looking into the pin, as soon as it becomes 0, makes this particular signal high, hold acknowledge signal high, saying that it has taken over, continue from where it has left by using both address bus and data bus. So, these are the 20 pins that has been available in 8086 microprocessor. Now, I have been mentioning about only one part of the pins that has been available. They are DN, DT by R bar, M by IO bar, ALE, interrupt acknowledge, write bar, hold acknowledge. Now, let us look at the remaining important points which is being mentioned, trying to say that what are the other pins that is being doing. Say when we try to talk about the address bus, we just mentioned that the address bus AD0 to AD15 is being multiplexed, and we have A19 to A16 address lines having status pin. Now, the status pin S5 and S6 are the interrupt enable. S5 is for interrupt enable flag bit that is updated at the beginning of each cycle. The status of that particular flag is indicated through this pin S5. It is being done during the remaining parts of the mission cycle. During the T1 state, we will have the address, the remaining state, this particular pin will have the status of the interrupt flag. S6 is again low. It indicates that 8086 is in control of the bus. During the hold acknowledge clock cycle, the 8086 tri-states the S6 pin and thus allows other bus master to take control of the bus. As I just explained to you, stating that the DMA operation is being done, the status of that particular bus being under its control is indicated by S6 pin, and especially it is done during T3, T4, T5 mission cycle, because T1 state is basically used by the processor for sending its address. When you talk about the S3 and S4 status pin, it can have 4 different combinations. These are combined together and performs the operation. When both are equal to 0, 0, it says that it is using the extra segment to access the data from the external world. When it is 0, 1, it is accessing the stack operation. That means that it is either pushing the data, or it is popping the data, or it is storing the data that is available in the register on the top of the stack, or it can be the flag register which is being stored. It can also be the code segment value which is being stored when there is a call or when there is an interrupt. When it is 1, 0, the code segment is being accessed. That means that it is now using the address lines and data lines, using the code segment to access the opcode from the memory location. The last one is when it is 1, 1, it accesses the data. It can be other than the code area and the extra segment area where data can be accessed. Now BHE bar S0. S0 is again a status pin, and which we know that BHE bar is being used for certain operations, especially for accessing the data from the memory location. We will discuss the operation of the BHE bar in greater detail when we try to talk about interfacing. For the time being, let us say that BHE bar is quite important. It is complement of A0 pin to perform the required operation. Whenever you want to access a 16-bit of data, and out of which the higher order 8-bit of data is being accessed when BHE bar is equal to low. When S7 signal is active low and floats to tri-state during the hold state. So that means that this is a pin which tries to say that the microprocessor is in the hold state when this particular pin is low. We have just looked into the read bar signal and test bar signal. I just said that we will discuss this particular signal later on. Test bar pin is used along with a signal instruction called as wait. Whenever the microprocessor executes a wait state, it tells the external world that the microprocessor is now supposed to control. So that means that the device which is externally connected to the microprocessor wants to access the bus and perform the required operation, and the program should not continue. This is being used for synchronizing the two instructions or two programs together. So we have here test bar pin which does the required job. I just mentioned about INTR, a non-maskable pin, and we discussed about reset, ready, clock, MNMX bar, and we looked into all these pins of minimum mode. Let us look into the maximum mode pins. In case of a maximum mode, we basically have the S0, S1 and S2 pin, S0, S1, S2 pin, which is now connected along with the DEN, DT by R bar, M by IO bar. As we have now in the maximum mode, these pins doesn't work as the signals is being generated. In the maximum mode, it works as S0, S1 and S2. It has 8 different combinations. One is interrupt acknowledge, the other one is read IO port, the other one is write IO port. When the system is made halt, it goes into a state called as T halt state. T halt state is different from T wait state, it is different from T hold state. It is a state where the microprocessor stays in that particular state until and unless there is an reset, hardware reset, or there is an interrupt. Only this is the 2 period of time the microprocessor comes out of this particular state, and the system will not know why the microprocessor is not working. To enable us to understand, we have those 3 pins that enables us to say that the microprocessor is in the halt state. Whenever it is trying to access the code, we have 100. When it is doing read memory, it has got 101. When it is writing the memory, we have 110, and when it is passive state, it has 111. Now instead of trying to talk about DN, DT by memory and IO bar, all the required signals are available by S0, S1 and S2 pins, that is having 8 different combinations. It will tell the external world what is being done. ALE pin is being used for something else in the maximum mode called as QS0 and QS1. So ALE is required, and automatically we need to really use certain logic to get these signals as if it is an ALE signal. QS0 and QS1 talks about the status of the queue. Why do you require the status of the queue? the Q status is required to the external world only when you are having a coprocessor. The coprocessor requires to know which instruction or what instruction is being executed. When we have a microprocessor working, it so happens that it is quite convenient for the processor to understand, saying that it is performing a particular operation. But the coprocessor is one which is being connected parallel to microprocessor. So when we are talking about 8087 coprocessor, these are being connected together, having a common data bus, address bus. I mean, I am not showing the demultiplexing and latches and other things. It's assumed that it's all there. I'm just trying to give as a bus as address bus and bidirectional data bus and bidirectional address bus. Now 8086 is the main processor which starts any program, or it tries to read any particular program. So it is possible to perform this particular operation because it is the main processor. Coprocessor has the same type of Q in it. So to make this particular coprocessor understand, stating that what is the status of the instruction it is being executed, we have 4 different combinations. When there is no operation that is being performed by the main processor, we have the value in the pins QS0 and QS1. It is not QS1 and QS1, it is QS0 and QS1, both saying that it is 00. QS0 is 01, it says that the first byte of the opcode is being fetched from the queue. See, this is an instruction which makes the device understand, stating that the first code is being brought. Once the first opcode is being brought, the same thing goes to the coprocessor as well as the main processor. The coprocessor also decodes it and finds out whether the code is 1B. If the code is 1B, it knows that that particular instruction is meant for the coprocessor, not for the main processor. To enable it to understand this particular process, we have here a code 1B, and this particular Q status will tell you this is what is happening. Whenever the microprocessor uses a jump instruction or when there is an interrupt, it clears the queue. Similarly, at the same time when it clears, even the coprocessor has to clear it, hence we have the signal 10 to empty the queue. The last one what we have is the subsequent byte of the instruction is being fetched from the queue, then we have the code 11, so that if it is not meant for 8087, it ignores it. These are some of the points which is being done by the microprocessor. We have a very important signal called as lock. Lock is being used along with a lock instruction. This it indicates to another system bus master not to gain control of the bus while this particular signal is active. That means that it is an external signal which is coming out of the microprocessor, telling the external world that the microprocessor is doing some special job. It is not going to relinquish the bus. If you are trying to talk about connecting multiple 8086 processors, this particular signal will be used. Example, when you are performing an exchange operation, which you know that we have a thing called a semaphore in operating system, and the same thing holds good when we are trying to talk about the operation in the hardware. We have a lock prefix instruction. The last 2 set instructions what we have is grant and request. This is similar to what we have mentioned regarding the DMA operation, which is being used in case of the 8086 microprocessor in minimum mode. So it tells that whenever it wants to relinquish the bus for the external device, the request has to come from the device. We have a hold. In case of the maximum mode, we have 2 options. One is the request 0, grant 0, and request and grant. So that means the same pin uses the operation of hold and hold acknowledge. The only difference is we have a higher priority for request and grant 0 and lower priority for request and grant 1. And with this we come to the end of the pin configuration of 8086 microprocessor. And you need to really understand, when I am trying to talk about all these operations, you have major 2 important points which I would like to summarize, trying to say that we have basically the 16-bit address lines which is multiplexed with data. The remaining address lines are being multiplexed with the status line S3 to S6. We have BHE bar signal which is being used by the microprocessor to interact with the external world, especially to access the higher order 8-bit of data when it is accessing 16-bit data. We have other signals which enables it to perform the required operation, and the most important part is the clock signal, which is having a 33% duty cycle, which enables it to perform satisfactorily. So, to generate this particular signal, we have a separate chip available. Without going into the details, I would like to stop about the pin configuration here, take up the remaining part trying to say that how do you program this particular device, what happens with the system, how does the system operate in the coming class. Thank you.